And folks, I know you must be exasperated with me reading to you, and I normally don't do that in class, but with this change, I really feel the need to emphasize a few points. And to be honest, this is the last chapter that we'll cover, so I feel okay. I need to touch base on just a few more things, and then we'll cool it with the reading. But the t distribution, let me touch base on what this is about. Every sample from a population can be used to compute a z-score or a t statistic. If you sample all the possible samples of a particular size and compute the z-score for each sample mean, then the entire set of z-scores will form a z-score distribution. In the same way, you can compute t for every sample, and the entire set of t values will form a t distribution. As we saw in Chapter 7, the distribution of z-scores for sample means tends to be normal, specifically if the sample size is large, or if the sample is selected from a normal population, then the distribution of sample means is nearly a perfectly normal distribution. In these same situations, the t distribution approximates a normal distribution, just as t approximates a z-score. How well a t distribution approximates a normal distribution, that's a typo there, excuse me, is determined by degrees of freedom. In general, the greater the sample size, the larger the degrees of freedom, remember it's just n-1, the better the t distribution approximates the normal distribution. The fact is demonstrated in figure 9.1, which shows a normal distribution and two t distributions of 5 and 20. So as I look at 5, it's flatter, and 20 becomes more normal and more like the z distribution. And of course, the normal distribution is pictured there at the top in those broken arrows. So this is, and let me just read the caption. And again, I know it's vexing to have me read, but I really want to touch base on these things. Distributions of the t statistic for different values of degrees of freedom are compared to a normal z-score distribution. Like the normal distribution, t distributions are bell-shaped and symmetrical and have a mean of 0. However, the t distributions are more variable than the normal distribution, as indicated by the flatter and more spread out shape, which they call platykurtic, incidentally. The larger the value of degrees of freedom are, or sample size, they go hand in hand, the more closely the t distribution approximates a normal distribution. So we're beginning to use this table, and I'm going to take a good minute or so to go over the table here shortly. But just as we use the unit normal tables to locate proportions associated with z-scores, we use a t-table to find proportions for t statistics. The complete distribution is presented in Appendix B, and a portion of this table is reproduced in Table 9.1. The top rows at the top, the two top rows of the table, show proportions of the t distribution contained in either or two tails, depending on which one is used. And we'll go through a lot of problems, 5 different problems that will really reinforce this. The first column of the table lists the degrees of freedom, which is just n-1 for the problem. If I have 8 participants, degrees of freedom is 7. If I have 25 participants, degrees of freedom is 24. Finally, the numbers in the body of the table are the t values that mark the boundary, just as we had with z numbers here in a second. So when I get to it here, here we go. Below are the critical values of t for n equals 4. Let's say I had a small sample size of 4. My degrees of freedom then are 3. And let's just say I had alpha of 0.5 one-tailed. Now, I hope you can follow this. Here are my degrees of freedom of 3. And then I want to say, well, proportion in one tail. Can I find 0.5? Sure. I find proportion in one tail, 0.5. And then I follow it down to degrees of freedom of 3. And sure enough, it's 2.353. Now, would that go on the right or left if it were a one-tailed test? The problem will tell me that. The problem will say increase, improve, augment, something like that. Or it'll say decrease or worsen or reduce. And in that case, that'd be on the left. But the interpretation is pretty direct. I know my degrees of freedom. That's the easiest thing to define. And then I just find the one tail row and follow that over. And once I find that 0.5 and one tail, just follow it down to degrees of freedom at 2.353. Now you notice that's higher than our old buddy 1.65. And in a sense, we get punished, if you will, for a low sample size. We have to overcome a higher t critical value than would have been the z critical value. but using the table is really not so bad.